Right, good afternoon, everyone. We will start up with the next topic, that is resonance. Okay. I don't know why only 140 had joined. We'll wait for just 1 minute. Right. We will start with the resonance. Now, resonance. See, we had just discussed we had completed with the transients. After transients, resonance. Now, resonance is said to occur in any RLC circuit. Okay. So, if all the three elements are connected in series, we call it as series resonance. If the elements L and C are connected in parallel, we call it as a parallel resonance. Okay. Usually the effect of inductance gets cancelled with the effect of capacitance, and the RLC circuit will behave like a pure resistive circuit. This is what is happening in a resonance circuit. Okay, and the main application of a resonance circuit is the tuned circuits. Okay, here we can tune the frequency of the LNC circuits, right? So this is the very important applications of resonance circuit, right? An AC circuit comprising of R, L, and C is said to be in resonance when the applied voltage and the source current are in phase with each other. Okay, this is a very, very important point. The applied voltage and the source current are in phase with each other. Okay, then only resonance occurs, right? At resonance, the power factor of the circuit is unity. Now, these are the features of a resonance circuit. Resonance occurs only if the voltage and source current are in phase with each other. If they are out of phase, then resonance does not occur. Okay. And at resonance, what happens? The power factor is always said to be unity. What is power factor? You know what is power factor, ma? How to define power factor? Chat box is open. Please post me how to define power factor. You've heard of the word power factor? How to define power factor? Only one answer I got. Gaurav has told me, right? Next, the strength itself is very less today. Hmm? Power factor cos phi. Okay. Now, how to define cos phi? Cos phi, you know, cos phi is equal to R by Z, right? Resistance by impedance. Now, that power factor is going to be unity. So, what does it mean? R by Z is equal to unity. R by Z is equal to 1. So, it is nothing but R is equal to Z. I can tell it like that, right? So, we are defining cos phi is equal to 1, right? Cos phi is equal to 1 means R by Z is equal to 1. R by Z is equal to 1 means I can cleanly tell that R is equal to Z. What is Z? Z is going to be impedance. R is the resistance. So the impedance of the circuit is equal to the resistance. So what happens? The circuit behaves like a pure resistive circuit. Okay. Resonance in series circuit is referred as series resonance, while the resonance in parallel circuit is referred as parallel resonance. Okay. So we will be reading about two resonance, series resonance and parallel resonance. First, we'll start up with series resonance. Resonance is very, very simple as compared to transients. Okay. It'll just have a derivation followed by small, small problems. If you are very thorough with the small, small formulas, you can proceed with the resonance. Okay. In the exam, if you're getting choices between resonance and transients, please attend resonance. Okay, resonance will be very, very easy. They will be asking a derivation, a bigger derivation, what we will be deriving it today, or small problems combined together. Okay, so resonance will be quite easy as compared with transients. If in transients they ask AC transients, they may ask derivations, okay, or problems for DC transients, right? Now, all are equally important, but this is the general thing, question taken up for exam. Now, series resonance. We'll start with series resonance. At resonance, power factor being unity, Z is equal to R. This is what I told you. Therefore, reactive part of the complex impedance must be 0, right? Actually, for a RLC circuit, how we write? For RLC circuit, impedance is equal to, Z is equal to, we write square root of R square, okay, plus we do not know which is higher, XL or XC is the higher. So I will write it as XL, XL minus XC the whole square, okay, or XC minus XL the whole square, whichever is higher, we will take that polarity, okay. So now in this, what they are telling, Z is equal to R. Now the series resonance, the condition is Z is equal to R. So Z is equal to R means what happens directly, XL minus XC is equal to 0. Okay, so XL minus XC is equal to 0 means I can clearly tell XL is equal to XC. Okay, what is XL now? What is XL? XL is nothing but the inductive reactance. XC is the capacitive reactance. XL is the inductive reactance due to the inductance connected in the circuit, and XC is the capacitive reactance for the capacitance, right? Now, formula, we are just substituting for XL and XC. XL is equal to omega L, right? What is omega? Omega is going to be the angular frequency. I can define omega as equal to 2 pi f, okay, where f is going to be the frequency of the circuit, okay. Omega L is equal to 1 by omega c, or I can write this expression as omega square, okay, omega square is equal to 1 by LC, okay, or by taking a square root, we can tell it as omega is equal to 1 by square root of LC. So this is the expression for omega. Omega is equal to 1 by LC at series resonance. Okay. Now let me call this as equation number 1. Now this equation number 1, what does it indicate? Now just substitute the value for omega here. Omega is equal to 2 pi f. Okay, so I will call f is equal to, I will write f is equal to 1 by 2 pi, okay, square root of L into C, right? Now what happens actually, if I vary the frequency for a, in a series RLC circuit, resonance can be produced either by varying the frequency, okay, either by varying the frequency or by varying the inductance and capacitance value. This is what this equation is, right? The frequency can be changed, the series resonance can be changed by varying the frequency or by varying the inductance and capacitance value. What does it mean? We are tuning the circuit. How are we tuning the circuit? To adjust the frequency, right? So this is how it is applied in the tuned circuits. Okay. Next. Right. Now we call that as omega naught. Omega naught is called as the resonant frequency, resonant angular frequency, and f naught is equal to omega naught by 2 pi. So we call this as 1 by 2 pi square root of LC. Okay, f naught is equal to omega naught by 2 pi, where omega naught is called as the, omega naught is called as the angular resonance frequency, okay, and it is measured in radians per second, okay, or f naught is going to be the frequency, right? Now let us go into the circuit. Let me consider a series circuit having resistance, inductance, and capacitance connected in series, okay. Now these three are connected across a AC supply, right? Let me call it as E volts. Okay. Now in this RLC circuit, when the current is in phase with the voltage, current is in phase with voltage means what? The circuit behaves like a resistance, right? Then resonance occurs. Otherwise, resonance does not occur. Clear? Now, for the circuit, I can write the equation Z is equal to square root of R square plus XL minus XC the whole square. And what do we know? We know for series resonance, cos phi is equal to 1. So if cos phi is equal to 1, what does it mean? If cos phi is equal to 1, R by Z is equal to 1 and R is equal to Z. This is the main condition. Okay. And XL is equal to XC. Now, we generally explain what is resonance and now we are going into series resonance. Okay. Now, XL is equal to XC means I am substituting omega R value for XL and XC. Right. So, XL is equal to omega RL and XC is equal to XC is equal to 1 by omega RC. Clear? Now, from this we can derive omega R value. Omega R is equal to omega R square is equal to 1 by LC and omega R is equal to 1 by root of LC. Okay. And what is FR? FR is equal to 1 by 2 pi LC. Now this FR is called as the resonant frequency. In some books it has been given as F naught. Okay. So F naught or F naught, FR we call it as the resonant frequency. At resonance in a series circuit, FR is equal to 1 by 2 pi the square root of LC. Now what is the effects of this resonance? We know Z is equal to R. What is Z is equal to R? Impedance is equal to resistance. Okay. Now what happens? So XL is equal to XC and Z is minimum. Okay. Z is minimum. These are the effects of resonance. Impedance is minimum. Okay. Now if impedance is minimum, what happens to current? I is equal to, we know the expression, I is equal to V by Z. Okay, if impedance is minimum, then what about current? Current should be maximum. That's what is given in the second point. The current is Z is minimum and the current is maximum. Okay, what about the power? We know power is equal to I square R. So I square R means power is also maximum because current is going to be maximum. So we write power is also maximum. Okay, next EL is equal to IX and EC is equal to IX, right? That we know already because the voltage across the inductor is IXL, voltage across the capacitor is IXC. At resonance, what happens? I is equal to IR. Okay, because we know the current is going to be maximum. That is the effect what we had discussed previously. As the current is very large, the resonant current will also be equal to that. And even EL and EC are also very large. Okay, so in RLC circuit at resonance, both E and I are in phase. So how do we call them? We can write it as E is equal to E angle 0 and I is equal to I angle 0. Okay, so this can be written like this. These are the effects of resonance. Okay, now coming to the phasor diagram. The phasor diagram, check here. We will draw the phasor diagram for resistive circuit, capacitive circuit, and an inductive circuit. Okay. Now this is more or less like a RL circuit, RC circuit, and RLC circuit. The same thing. Okay. Now see here, this is going to be a resistive circuit. The resistive circuit, what happens? XL is equal to XC. So if XL is equal to XC, I can tell voltage across the inductor is equal to the voltage across the capacitor. Okay. Now all this occurs at F is equal to F naught. F is equal to F naught only. The XL and XC value are equal. Otherwise, XL will be greater or XC can be greater. It depends upon the values of the inductance and the capacitance. Clear? Now, we have told this is going to be a resistive circuit. So resistive circuit means what is the next thing? The voltage and current are going to be in phase with each other, right? So I and ER are going to be in phase with each other. So we can draw the phasor diagram like this. So in the phasor diagram, we will be taking the current and the voltage across resistor in the x-axis as you draw for a normal RLC circuit. RLC circuit, when L and C effect is getting cancelled, you will draw a pure resistive circuit, right? The same phasor diagram is drawn here. Okay, and the voltage across the inductance always in the upward direction, voltage across the capacitance always in the downward direction, right? Now this is the resistive circuit. Next, let us consider for an inductive circuit. Inductive circuit occurs only when the frequency is greater than the resonant frequency. F is called the frequency of the circuit, and F naught is called as the resonant frequency of the circuit. Okay. Now, what is F naught? You know, F naught is equal to, we've derived F naught value is equal to 1 by 2 pi, okay, square root of LC, right? So what happens when F is greater than F naught, the inductance effect will be higher than the capacitance. So XL will be always greater than XC. Okay. And what about EL? EL is greater than EC. Of course, if XL is greater than XC, EL will be greater than EC. EL is the voltage across the inductor and EC is the voltage across the capacitor, right? Now, what happens here? The inductance effort is more higher than the capacitance effect. So the circuit, the phasor diagram will be like this. See the phasor diagram. You will draw the resultant current in the upper direction. Okay, like this will be drawn. This is for inductive circuit. Next, the third case is the capacitive circuit. Capacitive circuit occurs if the circuit frequency is less than the resonant frequency. Okay, resonant frequency, you know how to calculate. This is the formula. Okay, XL is greater than XC. So if XL is greater than XC, what happens? EC is greater than EL. Voltage across the capacitance is greater than the voltage across the inductance. So what happens? See the resultant current or voltage will be drawn in the lower side of the circuit, because here only we are going to have the capacitance voltage. So capacitance voltage alone is going to be higher as compared to the inductance voltage. Okay. Next, now what is acceptor circuit? We acceptor circuit, many times they had asked in a 2-mark mark. Acceptor circuit has the capability to draw heavy currents and power from the mains. Okay. Acceptor circuit, generally they put a acceptor circuit if power factor is lagging in the circuit. See, power factor, the range of power factor should be between 0 and 1. If it is equal to 1, then we can take the performance of the circuit to be very good. Okay. And if we take it as 0, if the power factor is 0, then we will consider the circuit has a poor performance. Okay. But power factor being equal to 1 cannot at all be possible, because this is the ideal condition. However perfect the machine is, the power factor can be near to 0.9 only. It cannot be 1. Okay. So 1 means it is a very perfect machine. It is an ideal machine. Okay. Ideal machine or ideal circuit is going to be, it cannot be produced, right? Very ideal without any losses, that cannot be produced, right? That type of circuit only has power factor is equal to 1. So always what we do in your projects, all what you will do, you will try to make the power factor to be nearly equal to 1, but not exactly equal to 1. It is not possible. Okay. Right. The reactance curves we have discussed. Okay. See the current and voltage curve, the phasor diagram we have discussed. The reactance curves, we have 3 reactance curve. Okay. 3 reactance curve is XL, XC, and XL is equal to XC condition. Now see here, this is XL. In XL, what happens? Whatever we have drawn here, similar to that we are drawing with respect to frequency. So if XL is plotted against frequency, this is for XL. Okay, XL is plotted against frequency. Okay, this is frequency. You get a curve like this. This is going to be in an increasing manner. It is a linear manner. XL will increase with respect to the frequency, because we know XL value. What is XL value? XL value is equal to omega L, or you can write it as 2 pi FL. So what is the relationship between F and XL then? If F is increasing, okay, then XL is increasing. Okay. This is the relationship between the inductive reactance and the frequency. Now, what about the capacitive reactance here? Capacitive reactance, this is Xc. Okay. Now, capacitance reactance formula is Xc is equal to 1 by 2 pi Fc. Okay. So, what happens here? If capacitance decreases, Xc increases. So, this is going to be inversely proportional. So, inversely proportional means the curve will be like this, like a tangent curve. Okay, hyperbola, you can tell. Now, when this both effect is going to be equal, XL and XC is equal to XL is equal to XC, then the reactance, the total reactance curve, this is the total reactance, XL minus XC, you will be getting a reactance curve like this. Okay. Next, selectivity. Selectivity. Okay, now selectivity. Now I told you this is mainly used in tuned circuits. Tuned circuits means you have to be selecting the frequency. Okay, frequency whichever is suitable for your application. Now for this selectivity, we call selectivity as Q. You would have read in electronic circuits or in some other subjects. We are more related about the bandwidth. Okay, what is bandwidth? You know, bandwidth is going to be the upper frequency limit minus the lower frequency limit, F2 minus F1. Okay, now let us draw a current versus frequency curve. Now, when I draw a current versus frequency curve, the series resonance curve will be like this. Okay, that is what happens at F0, the resonance occurs. Okay, so what we have discussed at F0, the resonance occurs means at F0, R is equal to Z. So R is equal to Z means the current is going to be maximum, right? So if you check here, the current is maximum at F0, right? It is at the peak at F0, right? And it increases and decreases on the other conditions. Now, let us assume two frequencies, which is going to have half the power as that of the original power. Okay. And we call that as half power frequencies. Okay. So half power frequencies, we consider two half power frequencies, F1 and F2. Okay. And the current at F1 is going to be I1 and the current at F2 is going to be I2. And this both are of course equal and we equate it to a single point I1 is equal to I2. Okay. Now with this we are going to derive an expression. F1 we call it as the F1 we call it as the lower half power frequency and F2 we call it as the upper half power frequency. Okay. So power at points I1 square R is equal to I2 square R because we know the current is going to be equal. Okay, and power at resonance, we call it as I square R. Okay, now what is this value? I1 square R is equal to I2 square R is equal to half into I square R because we have told it as half power frequency, right? So half power means I will write it as 1 by 2 of the existing power. What is power? Power is going to be I square R. See here, power is going to be I square R. So half power frequency, I'm just multiplying that by half value, right? Now, we've already seen from the diagram, I1 is equal to I2. Now, I1 is equal to I2 means I can write it as I by root 2. From this expression, I can write it as I by root 2. So, I by root 2 means I will go 1 by root 2 is going to be 0.707. Okay, so I1 is equal to I2 is equal to I by root 2. Okay, this is how you get it as I by root 2. See, we put it here also. I1 square R, we are equating both. I1 square R is equal to half into I square R. Okay, or I1 square is equal to 1 by 2R into I square R. Okay, or this will be simplified as half into I, or I1 is equal to I by root 2. This is what has been mentioned here. Clear? So this is equal to I by root 2. Now next, let us derive the expression. Let Z be the impedance at half power points. So what is the current? You know, current is always voltage by impedance. So we are putting it as, so we are putting it as I1 is equal to I2 is equal to E by Z. Okay. Now E by Z means, now this also we have derived I1 is equal to I by root 2. Okay. Now what is I by root 2? I is going to be E by Z. Okay. So I will put E by Z and Z is going to be R. Right. Impedance is equal to the resistance. So I will write it as E by R into root 2. Okay. So now what is equating this both? I can tell E by Z is equal to E by root 2 R, right? Or equating the denominators, we can tell Z is equal to root 2 R. Okay. Now what is this? Z is equal to root 2 R. What is Z? Z is going to be impedance. Okay. Now we know from resonance R cos pi is equal to R by Z. Okay. Or rearranging this expression also, I can tell 1 by root 2 and cos pi is equal to 0.707. Okay, so cos pi value is going to be 0.707. Now at half power points, what happens? The power factor is going to be phi is equal to 45, right? So at F1, power factor is leading in nature, and at F2, it will be lagging in nature. Okay, now from this, I can write Z is equal to root 2R. I will square this equation. Z square is equal to 2 into R square. Okay. Or square root of this R square plus XL minus XC the whole square is equal to 2R square. Okay. Or this will be, take the square of this. So this will be R square plus XL minus XC the whole square is equal to 2R square. And XL minus XC the whole square is equal to R square. Just simplifying the equation. And XL minus XC XL minus XC the whole square is equal to R square, or XL minus XC is equal to R at both F1 and F2. Okay, that is at half power frequencies, the reactance is numerically equal to the resistance. Clear? It is only numerically equal to the resistance. Okay. Now at F1, we will take it as minus R. Okay, because see, we are taking a square root here. We are taking a square root here. So if I take a square root, see, if I'm going to take square root of 4, I will just put it as plus or minus 2, right? So plus 2, I will take it for one case, and minus 2, I will take it for other case. So what I will do, at F1, I will equate it as minus R, and F2, I will equate it as plus. Okay. So first for F1, I will take, for F1, when I'm taking it as minus R, XL minus XC is equal to minus R, right? Now, what is XL minus XC is equal to minus R? Means I'm going to simplify and derive a small expression. What is XL? XL at F1, what happens? Omega 1 L. And at XC, we call it as omega 1 C. Omega 1 is the angular frequency at frequency F1, okay, is equal to minus R. Now, simplifying this expression, omega 1 square LC minus 1 is equal to minus omega 1 into RC, okay, or omega 1 square LC plus omega 1 RC minus 1 is equal to 0, okay, or this is going to be a quadratic equation. So I will substitute, apply the formula minus b plus or minus b square minus 4ac by 2a, apply the formula and find out the roots. So by finding out the roots, we can tell it as minus r by 2l plus or minus square root of r by 2l the whole square plus 1 by lc. Okay, so this is the value for omega 1. Okay, now for omega 1, we have derived from F1 expression. Okay, now see here, neglecting R by 2L square as compared to LC, because see, this value is going to be very less. R by 2L value, we are considering it as very less, and we will consider 1 by LC to be very higher. So omega 1 is equal to minus R by 2L plus 1 by square root of 1 by LC. Okay, now What is square root of 1 by LC? Square root of 1 by LC is going to be omega naught. So we will put it as F1 is equal to omega 1 by 2 pi. Okay. Or omega 1 by 2 pi means just divide the entire equation by 2 pi. So we call it as minus R by 4 pi L plus 1 by 2 pi into square root of LC. Right. Now what is F1? F1 is equal to, I can call this as F0. So F0 minus R by 4 pi L. Okay. So F1 value is equal to minus, F1 value is equal to F0 minus R by 4 pi L. Okay. Where F0 is equal to 2 pi LC. That's what we have substituted here. Okay. Now we had taken here minus R. And the next expression we will take it as plus R. So F2, we are taking it as plus R. So F2, at F2, XL minus XC is equal to R. Now XL value, you have to put it as omega 2L because this is considered at frequency F2. Okay. So omega, let omega 2 be the angular frequency. So we call it as omega 2 L minus 1 by omega 2 C is equal to R. Okay. Or solving this equation, you will get it as R by 2L. The solution is R by 2L. Omega 2 is equal to R by 2L plus square root of R by 2L the whole square plus 1 by LC. Okay. Or omega 2 is equal to R by 2L plus 1 by LC. Right? Or omega 2 is equal to R by 2L, R by 2L, R by 2L plus omega 1. Or rearranging, I can tell omega F2 is equal to R by 4 pi L plus omega 0 by 2 pi, or F2 is equal to R by 4 pi L plus F0. This is the final expression. Okay. What is F1 value? F1 we have derived it as F0 minus R by 4 pi L. F2 value F0 plus R by 4 pi L. This is the difference between F1 and F2. In F1, the circuit behaves pure like an inductive circuit, and F2, it behaves like a capacitive circuit. Okay. Now the bandwidth. Now we had found out the values for F1 and F2. 1 minute. F1 and F2. Next, we will calculate the bandwidth value. What is bandwidth? Bandwidth is defined as the difference between the upper frequency limit and the lower frequency limit. So we call it as F2 minus F1. Now, what is F2? You know, F2 is equal to R by 4 pi L plus F0. And F1 is equal to R by 4 pi L minus F0. Right? So F2 minus F1 is equal to R by 2 pi L. Okay, clear? So this is the value of the bandwidth. So we have now, the important formulas are F0 is equal to 1 by 2 pi into square root of LC, right? F2 value, you know, F2 is equal to F0 plus R by 4 pi L, and F1 is equal to F0 minus R by 4 pi L, right? And F2 minus F1. F2 minus F1 is equal to the bandwidth. Bandwidth is equal to R by 2 pi L. Clear? Now, we will be next moving into the quality factor. Okay. Quality factor, you would have read in some other subject, I think, but we will anyway go through it. Quality factor, the ratio, till this any doubts are there, no? The strength is very poor. The strength is 179. I do not know. By Diwali impact of Diwali, I think so. Till this any doubt, you tell me. Otherwise, I will proceed with the next one. Are you listening, Ma? Now, what is the status of the other subjects? Everyone is going to complete 5th unit. How is the status? Okay. Okay. Because with resonance, we will also be finishing up the 5th unit. current and phasor diagram. Okay. Right. I will just repeat this phasor diagram, then I will proceed. Right. Now see, you remember, if it is going to be an R circuit, this will be the phasor diagram. If it is going to be a L circuit, this will be the phasor diagram. And if it is going to be a capacitive circuit, this is the phasor diagram. No, sorry. This is resistive. This is capacitive. And this is inductive. Clear? So in a resistive circuit, we know the resistive circuit is possible when, see, we are talking about resonance circuit, and resonance circuit is possible only with AC supply when RL and C are connected in series. Okay. Now in a resistive circuit, what happens? The voltage and current are always in phase with each other. This occurs in a resonance circuit only at F is equal to F naught. F is the frequency of the circuit and F naught is the resonant frequency. Okay. Now, what is resonant frequency? We have derived the expression for resonant frequency. F naught is equal to 1 by 2 pi. Okay, 2 pi square root of L and C. Right? This is the resonant frequency. Now, when F is equal to F naught, what do you mean when the resonance, the current and voltage are in phase with each other, then what happens? It is a resistive circuit. So XL is equal to XC, right? So if XL is equal to XC, we have the voltage across the inductance to be equal to the voltage across the capacitance, right? So as the voltage and current are in phase with each other, we will draw the phasor diagram like this. Okay, normal resistive circuit phasor diagram. Okay, next. In an inductive circuit, what happens? F is greater than F naught. Okay, so F is greater than X naught. F naught means XL is greater than XC. So XL is greater than XC means the voltage across the inductance is greater than voltage across the capacitance. So what is the thing? What happens? The inductance means always in the phasor diagram you draw inductance in the positive side and capacitance in the negative side. That is because you have a J operator, right? So the phasor diagram will always be on the positive side. Okay. That is because XL is equal to omega L. Okay. So when inductance or frequency increases, the reactance value also increases. Okay. Next. So it behaves like an inductance. Next, at when F is less than F naught. So F is less than F naught means what happens? XC is greater than XL. So when XC is greater than XL, we can also tell EC. EC is nothing but the voltage across the capacitance. Voltage across the capacitance is also greater than the voltage across the inductance. Okay. So what happens? It behaves like pure capacitance circuit, and the phasor diagram can be drawn like this. Okay. It will be drawn in the negative side as the capacitance is going to be 1 by omega C. You have a J operator there because XC you will write it as 1 by J omega C. J omega C. Okay, now when this is brought to the numerator side, you will write it as minus J by omega into C. Right? Clear? Right. Now we will proceed with the next one. Next, we will be dealing with the quality factor. This derivation is very, very important. They will ask you to derive the value for bandwidth. Okay, this is very, very important, this derivation. Next, quality factor. Now, quality factor is defined as the ratio of F0 to F2 minus F1. What is F0? F0 is the resonant frequency. And what is F2 minus F1? F2 minus F1 is going to be bandwidth. Okay, so we can write Q value is equal to F0, okay, divided by bandwidth. Okay, this is also a very, very important formula. Q is equal to F0 by bandwidth. Okay. Now, F naught by, what is F2 minus F1? F2 minus F1 is going to be, we have derived here already, R by 2 pi L. Okay, so I will substitute that value. And rearranging this, I will get it as 2 pi F naught L by R. Now, what is 2 pi F naught? 2 pi F naught is going to be omega naught. Omega naught L by R. So Q value can be omega naught L by R. Okay, now, or it can be written like this: Q is equal to 1 by omega naught C into R, because omega naught L is equal to 1 by omega naught C. At resonance, how do we get this? You understand this? See, we write omega naught, omega naught is equal to 1 by LC. Omega naught square is equal to 1 by LC. Or you can write it as like this: omega naught L is equal to 1 by omega naught C. Okay. Now, you can write with respect to inductance means you can define Q as omega naught L by R. With respect to capacitance means you can define Q is equal to 1 by omega naught C into R. Okay. Now, from equations 1 and 3, what is 1? See, I will go to the first equation. Okay, 1 and 3. Okay, be comparing this both, I can tell, I can make a product of this both omega 1 value and omega 2 value. Okay, omega 1, what is omega 1? Equation 1. Omega 1 is equal to minus R by 2L plus square root of R by 2L the whole square plus 1 by LC. And what is omega 2? Omega 2 is nothing but R by 2L plus square root of R by 2L the whole square plus 1 by LC. Okay, now multiplying this both, we will be getting it as, the square root will be removed and we will be writing it as R by 2L the whole square plus, the square root will be removed here. We will write it as 1 by LC minus R by 2L the whole square. Okay. Now what is omega 1 into omega 2 then? This both will get cancelled, right? Positive and negative, this both will get cancelled. So you will write it as 1 by LC, or 1 by LC is what? Omega naught square. You know, 1 by LC is equal to omega naught square. This we have derived previously itself, right? Or you can write this as omega 1, omega 2 is equal to omega naught square. Okay. Or substituting for all the omegas 2 pi f. For omega 1, it will be 2 pi f1. Omega 2, it will be 2 pi f2. And omega naught, it will be 2 pi f naught. So substituting all, you can tell f1, f2 is equal to f naught square. Okay, this is a very, very important derivation. They will be asking you to prove that the square of resonant frequency is the product of the upper and lower half power frequencies. Okay, they will be asking you to prove either omega naught square is equal to omega 1 into omega 2 and f naught square, or f naught square is equal to f1 and f2. So this both is very, very important. Definitely you have to put the first diagram. What is the first diagram? The current and frequency diagram, right? What is the current and frequency diagram? This is the current and frequency diagram. The initial one. This is the current versus frequency curve. Okay, this is very, very important for series resonance. For the parallel resonance, this curve will be opposite. If it is going to be a parallel resonance occurs only for parallel circuits. The curve will be like this, an inverted V curve. A V curve. Okay, and for series resonance, it will be inverted V curve. Okay, so that's why the behavior also will be just opposite. The current will be minimum in a parallel resonance as opposite to that of the series resonance. Series resonance, the current is maximum, right? So it will be opposite here. So same way, from here you have to start up. Okay, you have to explain the diagram. You have to explain what is F1, what is F2, why we call it as half power frequencies. We call it as half power frequencies because the power consumed at F1 and F2 will be half that of the power consumed at F0. Okay, so that's why we call it as half power frequency. You have to explain what is half power frequency, and you have to definitely tell what is F1. F1 is going to be lower half power frequency and F2 is going to be upper half power frequency. Okay, definitely you have to explain about this and then proceed into the derivation. Okay, first you have to derive F naught is equal to 1 by 2 pi into square root of LC. Then move about with the others. Okay, now the last one, Q. We have derived now Q is equal to omega naught L by R. Or this can be written as what is omega naught? Omega naught is equal to 1 by square root of LC, right, into L by R, or cancelling this, you can tell Q is equal to 1 by R square root of L by C. This is again an important formula for your problems. Okay, so 4 important formulas. Q is equal to F naught by bandwidth. Q is equal to 1 by R square root of L by C. Then F naught is equal to 1 by 2 pi into square root of LC, right? And F1, F2 formulas. Okay, these are very important. Clear? Next, we will be proceeding with the problems for series resonance and then with the parallel resonance. Okay, now till this, any doubts is there, ma? Please post me in the chat box. You have any doubts, anything has to be repeated, you tell me, we will proceed. Is this clear then? Series resonance is clear. We will be continuing in the parallel resonance, which has the just opposite effect as that of the series resonance. Okay. And one more thing, ma, Monday afternoon between 2 to 2:45, your quiz for circuits and networks is scheduled. Quiz 2. Okay. From unit 4 and unit 5. Unit 4 and unit 5. Okay, so please prepare and try to attend the quiz in the stipulated time. Okay, because this will not be rescheduled again, so please try to follow the timing. What about other subjects, ma? You started taking up the quiz in other subjects? Have you started taking the quiz in other subjects, ma? Three subjects you completed, Gaurav? When did you complete, ma? Because there was a LMS problem, all right? When did you complete? Yesterday or today? Ma, just wait for 2 minutes. I will just clarify you and tell you. Just wait for 2 minutes.
Ma'am,
16th, ma. Not today, 16th. Okay, 16th between 2 to 2:45. Monday, ma. Monday, 2 to 2:45. Okay? Right. Okay. We'll continue in the next class, ma. Thank you. See, please communicate to your friends about the quiz because the strength has been very low now. 140 is only there. So please communicate to your friends, ask them to attend. Okay. Thank you. You can give.